I can introduce the next speaker, Matteo Gastaldi from Politecnico di Milano. Please, Matteo, the floor is yours.
Thank you very much, and good afternoon, everybody. First of all, thank you very much to Professor Marquez that introduced the problem related to the solution in order to avoid corrosion for 50 years and 100 years of service life. Because the topic of my discussion is related to the use of stainless steel rebar that are rebar that normally are used in order to prevent corrosion for environment in which you have problem related to chloride and you need to reach long service life. As Professor Marquez showed before, there is a problem related to the concrete cover that you need to guarantee the passive condition of steel rebar for a structure that have 50 years that is higher than 70 millimeters. This is not feasible because the problem is related to cracking on concrete cover, and if you consider 100 years of service life, the problem is higher. And so for this reason you have to consider other solution, and the use of the stainless steel rebar can give you the answer, just to give an idea about why we can consider to use stainless steel rebar. Stainless steel rebar have a higher corrosion resistance with respect to normal stainless steel rebar. Sorry, have a higher corrosion resistance with respect to normal carbon steel, and so with stainless steel you can consider to reach a higher service life and to have a corrosion limitation to a time that is higher than the normal time that you consider for carbon steel. The problem is that there is no only one stainless steel that is proposed in the market for the use in concrete, because there are several kind of stainless steel. This is something that is also reported in the presentation, in the first presentation of Papworth. And I thank you, Prof, for this introduction that helped me to say that there is several stainless steel, and this is the problem. It's not like for carbon steel mainly, that is more or less one type of carbon steel. It's not true also for carbon steel, but generally it more or less is the same. For stainless steel, you can have different kind of stainless steel. I don't want to go in detail related to this, but the traditional stainless steel that was used in construction, in reinforced concrete structure, generally are of two types: austenitic, sorry, I try to use this, austenitic stainless steel and duplex stainless steel. For austenitic stainless steel, that is related to the structure of steel, I don't want to go in detail. The most used is the 304L, that is the name that is used in the American standard. And this is a stainless steel that has a very high amount of chromium, around 80%, and an amount of nickel that is around 10%. Another austenitic stainless steel that is commonly used is 316L, that have also an amount of molybdenum that is around 2-3%. It's different from the type of this kind of austenitic stainless steel. And the presence of this alloy element affects the corrosion resistance naturally. There is another important question that is related to the amount of carbon that is very, very low. This is normal for weldable rebar. That is an important characteristic that you have to consider for the use in construction. And you have to maintain low the carbon content, because this can create another problem related to corrosion that is not normal. Pitching corrosion, that is corrosion that we consider related to chloride, but is related also to sensitizing of the steel. I don't want to go in detail related to this. Another kind of stainless steel that is used is duplex stainless steel, that is generally 2205, that contain a high amount of chromium, 22%, higher than the austenitic one, a lower amount of nickel, that is around 5%, an high amount of molybdenum and also nitrogen. This affects the corrosion behavior. This is traditional one. For region related to the coast, nowadays also other kind of steel are proposed in the market that is austenitic with low nickel and duplex with also no nickel. And this kind of stainless steel contain different alloy element that is different from the previous one. And in particular, you have manganese inside in some of this steel, and this affects the corrosion behavior. And then I try to go in detail related to this. But this different stainless steel have different corrosion behavior, and this is important to consider. When we want to design using stainless steel, it's important to consider that we have also an effect related to the difference in the corrosion behavior that is related also to the chemical composition of the steel, not only, but also to the chemical composition of the steel. Okay. So for this reason, we have to consider that when we design a reinforced concrete structure, we have a target that is related to the durability that we want to guarantee. And for this reason, we need to select the correct solution, so the correct stainless steel that we have to use in order to guarantee the service life. And generally, this is a selection that need to have a maintenance-free solution, because when we use stainless steel, we have an increase of the cost, because stainless steel has a cost that is higher than carbon steel, and this is important. So if we spend money to prevent corrosion, it's important to consider that we need something that guarantees the service life without problem of corrosion. So this is the reason why generally you have to make a correct selection in order to avoid corrosion for the target service life, okay? And if you want to make a correct selection, it's fundamental to consider that we need to evaluate the critical chloride content for the different kind of rebar. Generally, for application that is not concrete, there is a number that is used to evaluate the corrosion resistance of the stainless steel rebar. This number is called PREN number. This is fitting resistant equivalent number. This is a number that is used normally for application in which stainless steel is contact with solution, generally neutral solution or acid solution, and is work very well for this kind of application. This number is related to the amount of the main alloy element that affect the resistance to corrosion in this environment. That is the percentage of chromium, the percentage of molybdenum that have a higher value, and higher value with respect to chromium, that is because it's multiplied for 3.3. And nitrogen that have a very strong effect, but the amount of nitrogen that is normally present in the steel is very, very low. But you have an effect of this that is multiplied for 16 and 30. This is the 16 for austenitic stainless steel, 30 for duplex stainless steel. This is what is reported in literature. The problem is that when we move from neutral solution and acid solution to an alkaline solution that is related to what is normally present in concrete, PREN is not effective. So we cannot use PREN in order to have an idea about the resistance to corrosion related to the initiation of corrosion induced by chloride if you are in an alkaline environment, because the effect, for example, of molybdenum is lower than the effect that we have in a neutral solution. You can consider to use this kind of number to make a selection of the stainless steel if you are in carbonated concrete, in which the pH is not 13, but is a pH that is below 9, okay? So for the concrete that is alkaline, that is in the normal condition that we have, in a structure that is exposed, for example, to seawater, in which the high humidity that is present in this area don't help to have a fast carbonation of concrete, and in which also generally concrete with a low water cement ratio is used, so you have a low penetration of carbonation. It's not so easy to have carbonation as the sea surface, so it's easier to have alkaline condition, and in this condition it's not possible to use PREN number. So the problem is how to evaluate the critical chloride threshold for stainless steel rebar. And in the past, a testing solution was proposed in which that is proposed also for carbon steel, not only for stainless steel. Testing solution use generally solution that is alkaline solution that simulate pore solution, and electrochemical test, different electrochemical test, potential dynamic, potential static test was used in order to evaluate the corrosion resistance and to estimate the chloride threshold for stainless steel rebar in this condition. This kind of tests are the advantage that are rapid tests, and so can give you a result in a few days. The problem is that the chloride threshold that you can find in this condition is not the chloride threshold that you can find in concrete, because for example, the chloride content that you have in solution, the concentration of chloride that you have in solution cannot be directly converted in the chloride content that you have in concrete. And you have not also the effect of related to the interface that you have between concrete and steel. And so this is very important. And we have considered also this before in the previous presentation. And moreover, you can have also a misleading effect related to also to the ranking of the different corrosion resistance of the different stainless steel rebar. This, for example, is our test related to testing comparison between testing solution and testing concrete. And here, fastly, you can observe that, for example, these two stainless steel, one is austenitic one and the other one is duplex, seems to have the same behavior in solution because the result more or less are the same, but in concrete you have a very high difference in which you have a corrosion initiation in this stainless steel with 3% of chloride and no corrosion, also with an amount of chloride that is either of 8% in concrete for the 304L stainless steel. And so this is something that you have to take in account when you can consider to make testing solution. So it's not possible to have an idea about the critical chloride threshold in solution, and so we have to move to concrete. What's the problem? The problem is that you need a long time to have the initiation of corrosion in concrete when you have stainless steel, because stainless steel have a high corrosion resistance. For this reason, you need a very long time to reach the amount of chloride that is enough to create corrosion initiation on this steel. And so you need, if you make bonding tests, as we observed in previous presentation, it's not so easy to obtain the amount of chloride that still surface also after 2 years, 3 years of test in order to have the corrosion initiation. Just to give you an idea about the corrosion resistance of the different stainless steel rebar, I want to show you this diagram that gives an idea about a review related to the resulting that is obtained on literature related to test on stainless steel rebar, different type of stainless steel rebar. And here you have black steel and the reported range that is normally considered, and then we consider also before in the previous presentation that is around 0.41% of chloride as steel surface. This is the range of the corrosion resistance and the range of related to the chloride threshold of black steel in concrete mortar test specimen. And for stainless steel, you have value that is higher and depend from the different stainless steel that you have. So there are stainless steel that have a lower chloride threshold, and there are stainless steel that have a higher chloride threshold. So this to give you an idea. For the traditional stainless steel, that is 304L, 316, 2204 or 5, you can observe that you have a very high generally corrosion resistance with a chloride threshold that is also higher than 5%. That is an amount of chloride that is not so easy to find in the real structure. And for 304L and 316L, there is only one research study that shows a corrosion initiation that is around 3.5% of chloride, that is related to test of Professor Sorensen, if I remember well, that is related to test that is a test in which you have a polarization of the rebar, and plain rebar was used, not a rivet bar. So there is some difference. This is related to the test procedure. This result is related to the different test procedure that were used in the different studies and so on. And so you have to consider that the test procedure affects the result. This is something that we discussed also before in the previous presentation. This is very important. And so, as Professor Andrade told before, it is crucial to have to make a comparison, a correct comparison, to have a single test that we have to repeat in order to have an idea about the real in the test chloride threshold, and you can have something that you can use also for provision and so on. Moreover, it's important to consider that the critical chloride threshold is affected by a lot of parameters. That is not only the type of stainless steel, but fundamental corrosion potential, as Professor Andrade told you before, that is related to exposure condition, because corrosion potential is affected by the amount of oxygen that is related to the humidity content that you have in concrete, because humidity content generally is the main parameter that affect the presence of oxygen. Also the structure of concrete, but mainly the humidity content affect the presence of oxygen at the steel surface. Okay, so if you are in the deep of the sea without, the problem is related to the diffusion of oxygen, and so the amount of oxygen that reaches the steel surface is very low, and this creates an incredible change in the corrosion condition that you have. Okay, this is only to give an example. Then there is also temperature that is very important, that is crucial for the chloride threshold. Also, the concrete is fundamental, as also reported by the previous in the previous presentation by Melchester, for example. The presence of voids is fundamental, the pH of the concrete, the type of cement, and so on. And for stainless steel is fundamental also the surface condition of the bar. This is fundamental. And in particular, the presence of oxides, because the presence of oxide that is, for example, related to the mill scale that is not correctly removed from producer, or the presence of oxide that is related to welding or other oxide that can be present, can affect a lot the corrosion condition that you can have on stainless steel, and this can reduce a lot the chloride threshold that you have. Okay, so due to the problem related to the time that you need to have corrosion initiation on stainless steel rebar, the practical way that you can consider to use in order to have an idea about the resistance to corrosion of this rebar and the chloride threshold for this rebar, you can consider to use accelerated test. That is not the real condition. This is logic. It's an accelerated test, but you have to consider that accelerated test is normally used also in order to obtain also other parameter. For example, the diffusion of chloride in concrete that is used in the model sometimes is obtained using accelerated test. So accelerated test is something that is normally used for also for other kind of in order to obtain other parameters. Okay, so accelerated test in which you can consider to add chloride directly during mixing, and this help you to have a controlled amount of chloride at the steel surface in a very rapid way, and make an anodic polarization. So you use the circulation of the current in order to increase the potential. This is the logic. that in this way you can consider to have a rapid, a fast idea related to the initiation of corrosion of reinforcement, because you increase the potential, so it's easier to have the initiation of corrosion. When you make this test, you have an indication of chloride threshold that is not the real chloride threshold, but is the chloride threshold related to the test. Then you have to use parameter that help you to coefficients, sorry, that can help you to move from the chloride threshold test to the real critical chloride threshold. And this, for example, the test, it's fantastic, the result that Professor Merkes had showed half before, because this is very important. So if we have a result, for example, from a real structure, we can consider to use the result of the real structure in order to obtain the coefficient that help us to make this comparison from the chloride threshold in the test and chloride threshold in the real structure. Just to give you an idea about the possible test that accelerated test that is possible to perform, we can consider to, for example, to fix the potential value and change the chloride that is inside of the concrete specimen. It's very important, as Professor Andrade told before, to have a number of samples that give us a statistical, can give us a statistical evaluation. And so you can consider to repeat the test at a specific potential with different amount of chloride in order to have, for example, the first initiation of corrosion in one sample on 10, for example, in the amount of chloride Cl2, and then increasing chloride content. I increase the number of samples that is affected by corrosion till the amount of chloride that give the corrosion on all the samples that are under study. In this way, you can consider to obtain a distribution of the chloride threshold. If this test was is repeated for different potential, you can obtain the diagram that is also showed by Professor Andrade, that is the Pedeferri diagram that gives you the relation between potential and the content of chloride. And so you can consider to draw the Pedeferri diagram considering the condition that you consider as the limit state condition for the critical chloride threshold, that is, for example, the lower value that is equal to 10% of sample that is affected by corrosion, and this can help you to draw this diagram, and so you can obtain the chloride threshold for the different potential that you can have in the real structure, because you can consider to use the potential that you have in the real structure in order to have an idea about the critical chloride threshold that you can have in this condition. Another possible solution is to fix the amount of chloride and increase the potential, and you can obtain the same result. Okay. This is, for example, an example of some results related to laboratory tests related to this kind of procedure. This is the test in which we have different samples with a fixed amount of chloride, and potentially it's increased in the time with a step of 1 hour. So sorry, the increase of potential is 50 millivolts in step of one hour. So each hour the millivolts is increased by 50 millivolts. And for example, you can observe that if the amount of chloride is 3%, you have no corrosion. And it is also observed at the end of the test that there is no corrosion. With 5% of chloride, you start to have a change in the diagram, and this indicates the initiation of corrosion. And then you can observe that you have an increase of the current. This is the parameter that is measured in electrochemistry. It's not so important, but this increase of current means that you have initiation of corrosion. This is also detected at the end of the test. And so this is when you have the change in the slope of the diagram, you can detect that here you have the initiation of corrosion, the peak corrosion initiation. This is the parameter that is normally considered in electrochemistry. So if you repeat this test for a lot of chloride content, changing the potential and so on, you can consider to obtain the data to draw the ferrite diagram in this condition. So in test with change of potential of 50 millivolts with step of 1 hour. If you change the test, if you change the parameter of the test, for example, you've made a step of 12 hours, you can observe that you obtain another diagram that give you a initiation of corrosion to potential that is lower. This is normal because 1 hour probably is too fast. It's a test that is too fast, it's too rapid. If you make test that is not so rapid, you can obtain a peaking potential that is lower, that is more closer to the real condition. Then when you move from this condition in which you have a change in time of the potential to a test in which you fix the potential, you can consider to obtain something that probably is more close to what is present in the real condition. And so if you can obtain the statistical distribution of the chloride threshold with no corrosion initially, and the increase of the corrosion increases in amount of chloride, and then if you repeat this test also to different potential static test to different potential, this is static test of 24 hours, you can consider to obtain a diagram that is below the diagram that I showed you before. And so this can give you a lower value of potential in which you have corrosion initiation. This is something that probably is more close to what's happened also in tests with a long time of exposure that is very, very long. So the problem is how to, what's the potential that we can consider in order to make this test, and to evaluate this, the potential that can be considered for this test. We can consider to analyze the data related to the potential on real structure, and you can observe that you have in a real structure or also in laboratory test, you can consider to measure different potential in different conditions, atmospheric area, tidal zone, or splash zone and submerged area. You can have different potential, and if you move in the worst condition, that is the condition in which you have the higher amount of oxygen, you are close to 200 millivolts. And so this is the potential that can be considered in order to have an idea about the worst condition that you have in a real structure in which you can have that is related to area in which you have an high amount of oxygen. Then for the test, you have to, first of all, to decide what's the concrete that we want to use. Concrete or mortar is fundamental to fix the mix design. You can consider to use a standard mortar, for example. You mix chloride, and here there is a problem related to the type of chloride that you want to use, sodium chloride, calcium chloride, because we have different effects. With sodium chloride, generally you have a higher chloride threshold. With calcium chloride, you have a lower chloride threshold. This is what's happened. Stainless steel rebar have to be used in the condition related to the production and only degreased. So in this way, you can consider to evaluate the real chloride threshold, considering the real surface condition of the rebar. You have to repeat the test for a number of specimens that is minimum 10 specimen, so means 10 bars. And it's very important also to mask the end of the bar in order to avoid problem related to crevice corrosion. This is a problem related to the test generally. You have only to fix the time of curing. Generally, we consider a time of curing of seven days. This also to reduce the problem related to the leaching. That is also a problem related to a previous presentation of markers. And the polarization now 200 millivolts for 24 hours. We have to fix the temperature, for example, 23 Celsius degree. And at the end of the test, you can evaluate also the condition of the rebar with inspection. You have to consider that you have to, if you want to have the critical chloride threshold, you have to make the test for different amount of chloride. This is an example of result of one test. You can observe that in one sample you have an increase of the current, and this show that during the polarization at 200 millivolts, and this show that you have corrosion initiation after the test. You can observe the initiation of corrosion in the sample. So if you repeat this test for the different stainless steel rebar for different amount of chloride in this specific condition, you can obtain the distribution of the chloride threshold. And here, for example, I reported some result for two different stainless steel rebar, austenitic stainless steel with manganese, and 2304, that is another stainless steel that I showed you before. Naturally, if you want to have the result related to the real critical chloride threshold, you need to have information about the coefficient that help you to obtain this parameter, considering the result that you obtain in the critical chloride threshold related to the test. And so you need to have information about the effect that is related to the environment, the temperature, the cement type, the compaction, and so on. Just to give you an idea, this kind of test nowadays is present in two standards. There is a PREN that is European, is the pre-standard European standard that contains this kind of test, and is also present in a British standard. Thank you for your attention.
Thank you, Matteo, for your presentation. Is there any questions? Because there is a question in the Q&A.
Okay, just to give an answer to the question of Javier Sanchez, that is related to the different result that they obtain related to the critical concentration. Yes, this is logic, because if you consider different stainless steel, not only in chemical composition, but also in the surface condition, you can consider that this affects the results. So if you take a stainless steel that is produced by a producer and another stainless steel that is obtained by another producer, you can obtain different results. So for me, it's very important to consider that when somebody wants to consider the use of stainless steel, but this is true not only for stainless steel, but also for other things. But if you want to use stainless steel for your design, it's fundamental that you can consider to make tests on the stainless steel that you consider to use in order to evaluate if this stainless steel give you the correct performance that you need. Because it's fundamental to evaluate if you have this effect. If you cannot do this and you want to make a selection, a previous general selection, you can consider or to make tests in some different kind of stainless steel, or to use data that is available in the market. This is for a previous selection, but at the end, if you want to be sure, you have to make the test directly on the stainless steel that you want to use, because the surface condition also the stainless steel can affect a lot the corrosion resistance, and also the difference amount of alloy element that the producer used in the specific stainless steel can give you an effect, because you know that stainless steel have not only a percentage of the alloy element, but you have a range in which you can consider to have to obtain this kind of stainless steel with the correct content of the alloy element. So due to this presence of this range in the amount of chromium, molybdenum, and so on, you have also difference in corrosion behavior. This is logic. I hope that I answered to this question. Thank you.
Frank Papa, would you like to ask your question?
You talked about using mixed-in chlorides to obtain the critical chloride level. Does the mixing the chlorides in change the free to fixed chloride ratio? And does that then affect the critical chloride level?
Surely the addition of chloride in the mix changes the condition. This is clear. This is the reason why it's fundamental to evaluate also some coefficient that you have to use in order to move from the chloride ratio that you can find with the accelerated test with the chloride ratio that you can find not an accelerated test with methylene chloride. So you have to consider this. It's fundamental to have an idea also with tests that need a long time or real exposure test, so in a real structure, in order to have the coefficient that can help you to move from the accelerated test to the real chloride ratio. And this is fundamental, I think. And
second question is, I don't know much about stainless steel and its aggregation levels and the effect of saturation, but I did see somewhere that the stainless steel passive film requires oxygen to build up, and it just made me wonder whether the critical chloride level could be much lower below water because of the lack of oxygen.
No, this is true also for carbon steel. It's not, it's the same. No. You have to consider that when you use stainless steel, the oxide that is present on stainless steel is already present, because you need a nanosecond for the formation of the oxide scale of chromium oxide on the stainless steel rebar. So you have a very fast formation of this passive steel on stainless steel rebar. And so not so important, but this is important. I forgot to give you another comment related to your previous question that is related to the effect of mixed-in chloride. You can consider that probably the chloride that is mixed in can help you to have a higher resistance to corrosion of stainless steel. This is something that is reported in the literature. It is also logic, because you can create a stronger passive film on stainless steel with the mixed-in chloride. This is an effect that you can have. I think that also other people that is present here can give the same feedback related to this.
Thank you.
You're welcome.
Carmen?
Yeah, well, thanks for the presentation. It's interesting to see all the type of stainless steel. My question is also about the mixing with the chlorides, because not only you mentioned the question that you mentioned, but are you able to set the concrete with 5% of calcium chloride or sodium chloride? Because the calcium chloride accelerates until a certain proportion and after delays the setting. In that case, above 3 or 4%, the setting time is long. And however, I finish my question, you can make, I think that this is what Javier Sanchez is trying to tell you, you can soak the chlorides. I mean, you don't need to mix in. You can just apply a potential, and you, the potentiostatic test that I presented, you are introducing from outside. In that case, you don't need to add in the mixing for having high amount of chloride inside.
Okay, I start to give the answer to the first question, and I agree completely with your comment because it's logical. So if you add chloride, you have a very fast setting and hardening of concrete. And this is a strong problem during the test, during the casting of the sample. Okay, for calcium chloride, the problem is incredible. So generally, we use water that is maintained in the refrigerator in order to reduce the effect. First of all, we mix the chloride in water before the period that we maintain in cold condition the solution. So we have a solution with very low temperature, around 5 Celsius degree. This helps us to reduce the problem related to setting. And we use also admixture, super plasticizer that help us. This is the technique that we use because it's not possible when you have an amount of chloride of 5% of calcium chloride, you have a setting in a few minutes. So it's not possible to cast 10 samples. Okay, for sodium chloride, the problem is not so strong. Fortunately, sodium chloride have no strong effect on setting as for calcium chloride. So for sodium chloride is not a big problem. The sodium chloride give a chloride threshold that is higher than the chloride threshold that you can find in calcium chloride. That is a salt that give a strong effect because the sodium chloride have sodium inside, and so this probably help to reduce the problem related to initiation of corrosion. This is to answer to this question. For the second question. If you apply a current in order to move chloride, you have also the problem related that you apply a current to move chloride. So I consider this is a possible solution, and I agree to you that this is another possible solution. We move from a solution in which we have not the problem related to the circulation of a current, so we decide to mix it in chloride, in order to have a fast, to have the chloride that still surface in a controlled way and in a very fast way, because we mix the chloride, so we have the chloride that still surface. And we measure this also at the end of the test in order to be sure that we have not a change in the amount of chloride that still surface. This is the logic.
Thank you.
You're welcome.